All right, so let's talk about the chain rule. At this point, if you're up to learning about the chain rule, you've probably taken a lot of derivatives at this point, and the chain rule is just another tool you have for taking the derivative of functions in certain situations. So the product rule refers to multiplying functions, quotient rule, dividing functions. What does the chain rule apply to? So the chain rule is used when you have what's called a composition of functions. You should be familiar with composition of functions from an algebra class you've taken, or maybe if you've taken a pre-calculus class, those were definitely gone over in a pre-calculus class. So let's look at how to use the chain rule. So the chain rule says if you have a function h of x, and it can be represented as a composition, f of g of x, right? Then the derivative of h of x can be represented as the derivative of f, with the inside parts here still remaining unchanged, multiplied by the derivative of the inside stuff, the g of x. Now, that can be kind of complicated to understand. I think it's of the 4 rules you've gone through, like the power rule, quotient rule, product rule. This is definitely the hardest to really understand, right? And chain rule, the name is a bit ambiguous. I've heard it back in high school. My teacher referred to it as the outside-inside rule, which is, I think, a really good way of thinking about it. It's kind of its unofficial name. So what you're doing is you're taking the derivative of the outside stuff while ignoring the inside stuff. And then you're multiplying by the derivative of the inside stuff. So I think this will be best shown through our first example. So let's take a look. All right, so our first example is pretty straightforward. F of x is equal to, in parentheses, 3x plus 2, all raised to the 6th power. Now, this is a classic example of why chain rule is so useful, right? Because you could do this without chain rule. If you multiply 3x plus 2 by itself 6 times, you could just use power rule on whatever really long polynomial you would have gotten. But that would take like a super long time. Instead, we'll just use chain rule. All right. So chain rule says we need an outer function and an inner function. We need to identify what the composition is. So here, our outer function is this power of 6 right there, while our inner function is this 3x plus 2. Okay, so what would be the derivative of this outer function? Well, we would just use the power rule. That's how you deal with exponents, right? And just note that the inner function is always something that's not just x, right? If it was just an x, you would know you could just use normal power rule with it. All right, so I would bring the 6 to the front. And my new exponent would just be the original exponent minus 1. Okay, so keep in mind, this stuff on the inside doesn't change. That remains the same, right? The inside stuff has to remain the same. Now, we're only halfway done, right? We've done the derivative of the outside. Now we have to multiply by whatever the derivative of the inside function is, right? So our inside function, 3x plus 2. You should be, very comfortable with just taking the derivative of that, linear equation and get just the constant 3 as your derivative, okay? And then from here, you can easily just multiply the 3 and the 6 together, and your final answer would be 18 times 3x plus 2 raised to the 5th power, right? And that's your final answer. Much easier than having to multiply this out 6 times. Okay, let's look at another example. Okay, so our next function that we're going to look at is just f of x equals sine of x squared plus 2x. So first thing is to identify what our inside function is and what our outside function is. Typically, you can determine that by figuring out, whether something's surrounded by parentheses and another thing is being done onto that, right? Like in our first example, the power of 6 was being done onto this entire 3x plus 2 part. Here, the sign is being taken of this x squared plus 2x part, right? Since the sign is doing something to this must be the inside function, this must be the outside function. That's really the trickiest part about chain rule, determining what the inside part is and what the outside part is. Applying it isn't really that difficult. So let's just take its derivative. So the derivative of f of x should be the derivative of the outside. Now the outside is sine. Derivative of sine is cosine, and it's only cosine of x, but here we have an x squared plus 2, which needs to remain x squared plus 2. Like that. Now, we have to multiply it by the derivative of the inside function. And our inside function is x squared plus 2, and taking the derivative of that, we get 2x plus 2. And that would be our final answer. All right, let's look at another example. Our next problem here is another kind of classic problem for showing why the chain rule is so useful, right? So our function is 2x to the second plus 7x minus 9 in parentheses raised to the 60th power. Now you could multiply all that out, but you'd be insane to try. It's easier just to use the chain rule. Now, something you might notice is that the chain rule looks a little bit cleaner than some of the previous stuff like product rule and quotient rule. And it kind of is cleaner, but students typically have a harder time with this. The reason it looks cleaner is because you only need two things, right? For quotient rule, for example, you needed the original, like numerator, the derivative of that, the original denominator, the derivative of that, and then the original denominator squared. You needed 5 components. Chain rule, you just need 2. Derivative of the outside, and then the derivative of the inside. Right, that's why it kind of looks cleaner. We'll get into a little more, some more complicated examples in a bit where it kind of gets drawn out. So here, let's identify what's your outside function. So I see a 60th power, and then stuff inside of parentheses. So I can tell my exponent is my outside function. My inside function is this trinomial. All right, so derivative of f of x should be equal to the derivative of the outside function, which is 60 times, and all this inside stuff has to stay the same. You don't actually need to manipulate that in any way. And then you increment down your exponent. That becomes 59. And now that's multiplied times the derivative of the inside function. Right? So that's going to be 2x squared becomes 4x, 7x just becomes plus 7, and the negative 9 becomes 0. And that would pretty much be it. You might be required to multiply this out. You could, multiply this 60 into here, but typically it's not necessary. All right, so let's look at another example. Say we had something like this. E raised to the 3x. Okay, so you should be familiar with how to take the exponent, how to take the derivative of e, right? The constant, e to the x. So let's take a look. And I'm going to have that equal f of x. All right, so what is our inside function? What is our outside function? The first thing you're going to want to look for is when you're dealing with this and your exponent's up here, your variable's up here in the exponent, the base is typically going to be your outside function, with 3x being your inside function. Now, a lot of examples come up. I've seen a lot with having to take the derivative and using the chain rule with an e raised to some power. So let's take a look. So f prime of x is going to be equal to the derivative of your outside function, which is just e raised to a power. And e raised to a power, the derivative of that is just itself, right? It's unique in that way. And then it's multiplied by derivative of the inside stuff here, which the derivative of 3x should just be 3. So your final answer would be 3e raised to the 3x. Okay. Now we're going to look at some more complicated examples. Make sure you're able to do, stuff like this. Students have a lot of trouble with chain rule just because it's one of the harder ones to understand. But once you're able to, quickly identify what the outside function is and what the inside function is meant to be, then chain rule starts becoming easier. And it makes things so much quicker. Let's look at some other examples. So here we have a slightly messier, more difficult chain rule problem. Our function here is f of x is equal to ln, natural logarithm, of cosine of x squared minus 7 in parentheses raised to the 6th power. Right? And this type of type of equation isn't necessarily rare. You could encounter this kind of thing plenty of times, right? What makes this problem messier is that you don't just have one composition of functions. You have multiple, right? This natural logarithm is your first function, and then inside of that you have a cosine function, which inside of that you have this power function, and then inside of that you have this binomial that also is differentiable, right? So here's how you go about dealing with that, okay? So it's still the chain rule. You're just applying it over and over and over until you get to the most inside function. So this is what that kind of example would look like. So f prime of x, derivative of f of x. So first rule, all right, let's take the derivative of the outside, which it's just ln of the inside stuff. And the derivative of the natural logarithm is 1 over x, except our x stuff is all of this. Cosine x squared minus 7 to the 6th power. Right? But we're not done. We did the derivative of the outside. Now we have to do the derivative of the inside. Multiply it. Okay? And a lot of times you'll see, to differentiate something, you'll see dy dx or something like that. So we still need to take the derivative of all this stuff. Cosine of x squared minus 7 raised to the 6th. Okay? We still need to take that. So what's the derivative if we're only looking at this? Well, let's apply chain rule again. We have an outside function and an inside function. Okay? Now, all this stuff just comes down along with everything. So I'm going to continue on with the 1 over cosine x squared minus 7 raised to the 6th. And I'm going to eventually run out of room, like you do with a lot of these problems. Let's take the derivative of this. So we have to take the derivative of the outside stuff and then multiply it with the derivative of the inside stuff. The outside thing's a cosine, right? Cosine of x. The derivative of cosine of x is negative sine of whatever's on the inside, which in this case is x squared minus 7 to the 6th. And then multiplied by the derivative of the inside stuff. And the inside stuff in this case is x squared minus 7 all raised to the 6th. Okay? Now all this stuff gets carried down while we take this derivative. So here I still have my 1 over cosine x squared minus 7 raised to the 6th multiplied by negative sine of x squared minus 7 raised to the 6th. And now I have to multiply by the derivative of x squared minus 7 all raised to the 6th. Now this is very similar to the previous examples we did. This is an easy chain rule to compute. The outside is this power of 6, which now becomes 6 multiplied by x squared minus 7 to the 5th. And we have to multiply by the inside stuff, d over dx of x squared minus 7, right? And now we just have to do one more step. All of this stuff carries down. 1 over cosine x squared minus 7 to the 6th multiplied by, right, I use parentheses also, but sine x squared minus 7 all raised to the 6th times 6 times x squared minus 7 raised to the 5th times the derivative of x squared minus 7, which is just 2x. Now, I'm not going to deal with just condensing all this. It should be something you're familiar with. And on a lot of exams, you might not even be required to multiply everything out. But that's how you would do, a chain rule where your function is multiple composite functions. You're just doing multiple chain rules, right? You take the derivative of the outside thing, and then you take the derivative of the outside thing one level in, then you take the derivative of the next level and the next level until you get down to that very center function. In this case, it was the x squared minus 7. And you end with this. All right. Hopefully that wasn't too confusing. It's stuff like this that makes chain rule one of the harder things to really get. However, chain rule is the thing you're going to encounter so many times, right? It's the derivative rule you're going to use the most out of anything. That and power rule, I guess. So let's look at one more example. For our final example, we have this. F of x is equal to the square root of 2x plus, and then in parentheses, 3x plus 4x squared, and then that's all to the third power. Now, first thing you want to do when you see a square root and you need to take a derivative, you want to change it to an exponent, right? You should be familiar with changing roots into like fractional exponents. So this is going to end up being everything in parentheses, 2x plus 3x plus 4x squared. And then that's to the third. And then everything is raised to the 1/2 power. Now, let's go on using chain rule, right? This is another example of multiple composite functions and multiple chain rules being needed. F prime x is equal to derivative of the outside function, which I think we can see is that 1/2. So we bring it to the outside, 1/2 times whatever's left inside, which should all remain the same, 2x plus, and then in parentheses 3x plus 4x squared, all raised to the third power. And then our new exponent is negative 1/2, multiplied by the derivative of what's left inside, d over dx of 2x plus, then in parentheses 3x plus 4x squared, all raised to the third power. All right, so that's our first chain rule done. Now we need to do another chain rule here, okay? So this stuff up front gets brought down, right? So 1 over 2 okay, and now we take the derivative of what's inside. Okay, now what's inside here is essentially a to the third power plus another constant, plus another kind of term, right? So what this would be is the 2x just becomes a constant 2, right? And then that gets added to the derivative of this portion, which the 3 comes down to become the coefficient. The insides all stay the same, 3x plus 4x squared. And your exponent is now 2. Okay, so that's the outside portion. Now we need to multiply by the inside portion, which is that 3x plus 4x squared. Okay, so that's going to look something like this. So that's going to be multiplied by d dx, and then 3x plus 4x squared. Okay, and our last thing, 1/2, like everything gets brought down and we just have one more derivative to compute. X squared plus 3x plus 4x squared to the third, then multiplied by 2 plus 3 times 3x plus 4x to the second, all raised to the second. And then finally, this should be multiplied by the derivative of 3x plus 4x squared, which is 3 plus 8x. All right, and that should be it for that example. Really, this is going to come with practice, getting used to doing any of the, derivative techniques, using any of the rules. You get better at it with practice. Unfortunately, that's kind of the main way to get better at calculus. Okay, so let's just review. So the chain rule is going to be your most used derivative rule. It's the type of problem you're going to encounter the most. And it also happens to be kind of one of the more complex rules to go through. So just remember it as the inside-outside rule. Remember to identify what your inside function is, what your outside function is, and just take the derivative from the outside going inside and then multiply what you have. When you're dealing with the more complicated examples like the last two we dealt with, work your way, like I said, from the outside in. And that should be pretty much it. You might need to go through this video a few more times to really get it, and I highly suggest just doing a bunch of practice problems to make sure you're able to identify when the chain rule is used. If you have any questions, throw it down in the comments. But other than that, good luck, guys.